Now this time what we've got is a chord and a line from the center to the chord, and we want to see what happens at particular times. Now, not much is happening with it at this moment, but once I start to get to a point where I'm going to try and get it in the midpoint, so I'm trying to get EC and DE to be equal. So, not as easy said than done. I'm probably going to be out by 0.01. So I think that's the best I'm going to be able to do. So I've got them pretty close. I'm really close to there. And it's really keeping in mind what the theorem's going to do and when I've got it, when we talk about it exactly. But it's a bit hard with this type of program to try and get it exactly there. If it's possible, I'm not sure how to do it at the moment. So let's measure the angle and see what happens to the angle here. So if I'm going to measure this angle here, and it's giving me the wrong one I want. I'm still getting used to this program. It's called GeoGebra. If you're looking to use it, it's a free program, so you can get it. We'll talk about it in class. So if you have a look there, the angle that it created is 90.05. Really what we're looking to do, it causes a 90-degree angle there. So once we get a chord and we bisect it, the line that bisects it will be perpendicular. So we get the point there to the line. Once it's a bisector, it will be a perpendicular bisector if it comes from the center of the circle to the chord. Now you could use that and extend it through if you want to use a radii as well. So a radius there that bisects the chord there will be a perpendicular it will cause a 90-degree angle to occur. Now why is that the case? Well, let's have a look at our actual theorem and how it works. So from there, if we get a situation, so we're working at the idea if it's perpendicular, start off that it bisects it. So if we have given the situation that ABO and CBO are 90 degrees, so we've got this line and it's perpendicular to the chord. So if we do a little bit of construction, we construct those two sides. Now notice they're both going to be radii. They're going to be equal. Now, because that's 90 degrees, and we know that AO and CO are both equal radii, and we also get another line that's equal to in both triangles, so OB is common to both. Then because our right angle, our hypotenuse and our side that are common, we get a congruent triangles, which means the third side must be equal as well. So there's our bisection. So AB and BC are equal because the congruent triangles, and those two sides must be equal. So the perpendicular line cuts the chord in half. It bisects it. In the converse of that theorem, so what if the line here cuts it in half? So we're starting with that. We want to prove that OB and AC are perpendicular. We get 90-degree angles there. So we know AB equals BC, because that's given. We're told that. We're starting with that. Then we know that AO and BC are equal because they're radii. So we can write equal radii. And again, OB is common, which means that all three sides in one triangle are equal to all three sides in another triangle. So by side, it is the same. It is congruent. The triangles are congruent. So that means these two angles there must be equal. And because they're along a straight line, they're supplementary, then they must, both of them add up to be 90, but they're the same, so twice that angle gives us 90. So it means they're perpendicular. So there's the proof of the idea when a line is drawn from the center to a chord. If it's perpendicular, then it bisects it, or if it bisects it, then it must be a perpendicular. We get that perpendicular bisector.